Let's briefly talk material balance calculations, all of the things that you basically need to know going forward as we calculate and do problems. We've already seen examples of problems, but let's kind of make everything a process so that you have a way to solve problems moving forward. So all material balances, they're all a variation on the single thing. You're given some input and output variables. You need to derive and solve equations using other variables, right? And so not derive like derive from calculus, but write equations, right? That makes sense based on your process flow diagram. So we've already seen some flowcharts and we've already talked about kind of how you put the flowchart together. But basically, it's used to organize information to calculate variables in a process. Boxes are processes, arrows are flow. So a box is a process, an arrow is a flow. Okay? That's just standard convention. All right? Now, as we go forward, we've talked about labeling a little bit in class, but here are some suggestions that I have to make sure that we're all talking kind of about the same thing. Write your values and your units of all your known stream variables, right? These are flows right here at the location on the chart, right? So don't write the flow that goes in somewhere near the output, right? Write it near those diagrams, and again, make big flow diagrams. Then assign algebraic symbols to unknown stream variables and write these variable names and their associated units on the chart. Okay. Many people like to just put the numbers and go forward, but if you can show me algebraic, it's much easier for me to follow your work. Remember that mass balances can be solved many different ways, so I need to be able to follow your work. And I'm not going to go and look for how you define the number, I'm going to look for your algebra. Okay? Then keep the number of labeled unknowns to a minimum. So this is like when we said that x of a plus x of b is equal to 1, right? The sum of the mass fractions is equal 1. Instead of having xa and xb on the diagram, we'd have 1 minus xa, right? That's a way of minimizing the number of unknowns. So in terms of consistent notation, let's just make sure there's a couple things that we want to do on all of our process flow diagrams. You can call it A, B, 1, 2, whatever works for you, but the one thing that needs to be consistent is some of this notation that we're going to fill in here. So first, M is always a mass, N is always a number of moles, and V is always a volume. Okay, these don't change. This is a capital V. Just make sure that it is a capital V. Later on, we'll use little v for velocity, but not right now. Okay, and then anytime it's a mass flow, it's an M with a dot. So that's mass flow. Anytime it's an N with a dot, molar flow. And anytime it's a V with a dot, that's volumetric flow. So these are the things that need to be consistent from problem to problem, okay? Everybody needs to use N for mass, everybody needs to use N for moles, so on and so forth, okay? Your subscripts can change based on your specific problem, but these need to be the same. Deal? All right. So a couple other terms that we need to know. The word scaling refers to a procedure of changing all the values of a stream, amounts or flows, by a proportional amount, so like scaling down by 2, while leaving the stream compositions the same. Okay, so this is important. If we have a scale down problem, what's changing is the amounts or flow rates, but not the composition. So if it's 50% methanol and 50% water, that stays the same, but the flow rate of that mixture can change. Okay, scaling up means that your final stream quantities are larger, scaling down means they're smaller. Kind of intuitive. You can't scale masses or mass flow rates to molar quantities by multiplication. You can scale mass to mass, but you can't scale mass to moles because we have to go through molecular weight, right? So you can't say that if the mass flow rate is 2 times, that the molar rate is 2 times. So you can't say that 2m dot is equal to 2n dot because you have molecular weight involved there. Okay, so that's important. We've talked a little bit about a concept called basis of calculation. And all that means is that the amount m or n, or the flow rate m dot or n dot, of one stream or stream of component in the process is a basis of calculation. So we've talked about having a basis of calculation of 100 grams, or maybe something that's given in the problem statement. We're going to talk about this as we go through problems. Basis of calculation is just basically it's a reference point as we go forward. That's really critical. Okay? Let's really quickly talk about balances on non-reactive processes. We're going to do something called degree of freedom analysis as we go through the semester. So I just want to talk really briefly about this. When we're balancing non-reactive processes, the max number of independent equations that can be derived by writing balance is equal to the number of chemical species in the input-output streams. So if you have A and B, that means that you can only write two independent equations in that case. Okay? We can write balances that involve the fewest numbers of unknown variables, and that's kind of the way that we wanted to go about balancing non-reactive processes. Okay, so if we're balancing non-reactive processes, you write two equations, one for A, one for B, and then write balances to solve. Now, you may say, well, what about the total? We talked about the total. Well, the total involves both A and B, so it's not independent because it involves both. All right. Let's talk real quick about degree of freedom analysis. And we're going to do examples of this in class. So let's just learn the concept now. Degree of freedom analysis helps to determine whether or not there's enough information to answer the problem. So yes, it is possible that you cannot solve a problem in this class. Okay. So degree of freedom analysis is a tool to help us determine whether or not we have enough information. How do you perform it? You draw and completely label a flow diagram, you count the number of variables, and then you calculate the number of independent equations. Okay, so draw a process flow diagram, figure out what your variables are, figure out how many independent equations you can write, and we'll do this in class. Okay, if your number of degrees of freedom is equal to 0, there are n independent equations in n unknown, and the problem, in principle, can be solved. So basically, this is the case where we've got enough information, just enough to go ahead. Now, if the number of degrees of freedom is less than 0, there are more unknowns than there are independent equations, and then we at least need to come up with additional variables to determine. Right now, this is hard to solve. We can also have a number of degrees of freedom greater than 0, and that means there's more independent equations than unknowns, and we may have maybe incorrectly labeled something, or there's more equations than we need. Okay? When we're writing mass balance equations, right, these are the sources of equations. This is where we get our independent equations. We can write material balances, energy balances, process specifications. So this is relationships between variables. So this is something like density equals mass over volume. We can also write physical properties and laws. So we can use something like the ideal gas law, PV equals nRT. For problems, we can use physical constraints, and we can use stoichiometric reactions. So these are where our balances are going to come from, our equations to solve all of our problems. So far what you've seen is you've seen material balances, and that's it. But we can also use all of these things to help us solve problems. Last thing for this particular lecture, this is the general procedure for a single unit process material balance calculation. So this is what we've been doing. This is just a way to formalize that. Okay, so the first step, you choose a basis of calculation, the amount or flow rate of one of the process streams. You draw a flow chart. You fill in everything that you know, including the basis of calculation, and give me whatever your unknown variables are algebraically. Express what the problem statement asks for in terms of variables. So that's writing something like M1 plus M2 equals M3 variables, right? If we're given mass and moles, make sure that we're in one basis. So you can't solve equations that have both masses and moles. You need to pick either mass and mole and then convert everything to mass or mole. You also need to perform a degree of freedom analysis. And again, we'll have some examples of this. Write out your equations, combine circle variables to solve for, and then do one of our validation steps. try and substitute, and then solve for anything additional in the system. All right, so that's some general information about how to set these problems up. This is a good kind of stepwise guideline for you. This would be a good checklist to use anytime that you're solving a problem.